Hello, welcome back to another episode of Math with Haas. You're watching Precalculus Season 2, Episode 21. We're continuing our investigation of trigonometry, and in particular, we're continuing our discussion about inverse trig functions. So, in the previous two episodes, we looked at the inverse sine function and the inverse cosine function. And what we want to do now is look at the inverse tangent function. And if you watch the two previous videos, then you'll see that the themes here will suddenly look very, very similar, but there is going to be a surprise difference. So, in this case here, we have y equals tangent x. Our question is, what is the inverse function? So, by definition, for the inverse tangent function, so definition inverse tangent function, the definition says this, so x is going to equal tangent y. So what happens is the x for y equals tangent x, the independent variable, the input, is now going to become the output for inverse tangent. And similarly, the output for tangent, the y, now becomes the input for inverse tangent. So that is the definition. Now we want to look at notation. So notationally, you'll see this here going on with a -1. So as I've mentioned before in the two previous videos, this -1 refers to the fact that we're discussing, strictly speaking, the inverse tangent function. That is not an exponent, that is not a power of a -1, that is referring strictly to the inverse tangent function. Now, we do have this old school notation with this ARC, and how we would say this is arctangent of x. So this will be the notation I use, and this is what I will use whenever I refer to the inverse tangent function. I'll call it arctangent because that just rolls off the tongue nicer. So arctangent of x, just like with the arctangent of sine and oh wait, no, that's an arctangent. I meant arcsine and arccosine. So just like with arcsine, arccosine, what we're going to do is look at a table of values to generate a graph for arctangent. So we have y tangent x, and we'll have y and arctangent. Alright. So what we want to do is think about inputs and outputs. So if I plug in a 0 in for tangent, remember tangent x is equal to sine over cosine. So this is really saying what is sine of 0 divided by cosine of 0. Sine of 0 is 0, cosine of 0 is 1, so we get 0. So if I plug 0 in for arctangent, I'm going to get out 0, because the output becomes the input, and the input becomes the output. So if I plug in, say, pi over 4, well, sine of pi over 4 is square root 2 over 2. Cosine of pi over 4 is square root 2 over 2. So if we have tangent of pi over 4, that's going to be square root 2 over 2 divided by square root 2 over 2. And that is just a number divided by itself, which is 1. So if I plug in 1 into arctangent, I get out pi over 4. So to kind of illustrate this, tangent of pi over 4 is equal to 1. And so arctangent of 1 is going to equal pi over 4. This output becomes the input. And so then the original input for tangent becomes the output for arctangent. And we can continue this, right? No, we can do something different. How about 2 pi over 3? Well, sine of 2 pi over 3 is square root 2, or square root 3 over 2. Cosine of 2 pi over 3 is negative a half. And so we get negative root 3. So if I plug in negative root 3, I'll get 2 pi over 3. Now, I can be tricky and mess with you now. If I were to pick, say, not 3 pi over 4, let's see. If I pick 5 pi over 4, then I would actually get out a 1, because sine and cosine both give you negative square root 2 over 2. So we get positive 1. So if I plug in 1, I should get out 5 pi over 4. But just like in the previous videos, we have this problem where the same input gives you 2 different outputs. And that is, again, because of our x and y coordinates on the unit circle are associated with an infinite number of angles. Each x, y coordinate pair has an infinite number of angles and their coterminal angles associated with them. And so that means that we get this problem of our functions not actually being functions unless we do some sort of range restriction. Alright. We'll see more of that here in a moment when we look at the graph. Now, there is a kind of plot twist, right? Because if I plug in pi over 2, well, sine of pi over 2 is 1, but cosine of pi over 2 is 0. 1 divided by 0, is that 0? No, it's not. That is, we would normally say undefined, and usually when you divide by 0, that means a asymptote is involved. In fact, we saw that, right? So let's think about it this way. So if we were to graph just tangent, this is our nice graph, and then we had this problem here. So this would have been pi over 2, this would be negative pi over 2. At both these x values we had an asymptote because you cannot divide by 0. And in fact, if you kept adding multiples of pi to pi over 2, or subtracting multiples of pi, you would get you would generate all the other asymptotes because there's an infinite number of asymptotes. So essentially what we have going on here is this same problem, but now our asymptotes are going to be horizontal asymptotes instead of vertical. So this is going to become rather interesting already, right? Because we have this situation going on where we have our horizontal asymptotes. And the reason why we have horizontal asymptotes is because you cannot, well, when we think of the long-term behavior here, right, as our inputs here get closer and closer to pi over 2, they go off to infinity. So since the outputs and inputs are swapped, as our inputs get larger and larger towards infinity, the outputs have to be getting closer and closer to this asymptote, right? Because the inputs and outputs are swapped in regards to tangent and arctangent. So in other words, what I'm saying is as our inputs get larger and larger, our outputs have to get closer and closer to this horizontal asymptote at pi over 2 and negative pi over 2. So we can note we had 0, At 1, we had a pi over 4, so that's this right here. Now, let's see, this is 1. How do we get a negative 1 though? What happens if I plug a negative 1 in? So if I plug in a negative 1, we can get out, say, 3 pi over 4, 7 pi over 4. Those are possible, right? If you plug in 3 pi over 4, 7 pi over 4, you get out negative 1. But if we look at our graph here, I want to be able to draw the line seamlessly. So I mentioned already that the long-term behavior is going to get closer and closer to infinity. And so if I wanted to draw this out like so, right, as it gets closer and closer to infinity in this direction, if I want to know what this point here is, we have to go negative pi over 4, because when we think about the two values I talked about, 3 pi over 4 and 7 pi over 4, those are way up here, right? And we want something that's right down here. So, if we recall our unit circle, if we go in the clockwise direction, that's the same as a negative angle. So, this angle here, if we go positive, that is a 7 pi over 4. But if we go in the negative direction, that is clockwise, that is just a negative pi over 4. So that's why we get this point here. Alright, that is a very terrible looking arctangent graph. So we're going to use Desmos. We could plot more points, but we kind of talked through the basics of the graph, so we're going to now look at it on Desmos. So here's Desmos. So here's x equals tangent y. Now, let's see here. Let's get y equals pi over 2. We'll need to change that color. There we go. And y equals negative pi over 2. Oh, perfect. That looks nice. So, this portion here between our two purple lines, that is our arctangent and our two asymptotes. Now, because every xy coordinate pair is associated with an infinite number of angles, remember that the inverse trig functions give out angles as outputs. So if we do not do a range restriction, we get a infinite number of values, where if I plug in some x value, I get an infinite number of outputs, and that is not good because this fails the vertical line test. So as is, when we just switch the x and y's in accordance with our definition for our arctangent, it's still not a function yet. We have to apply a domain restriction, and we can see there's a very natural domain restriction here. I did it again. I said domain when I meant range. So that's now 3 videos in a row where I made that same mistake. That's hilarious. So what we want is the range restriction. And there's a very natural range restriction if we restrict the range between negative pi over 2 and pi over 2. In fact, that's how arctangent is normally defined. Okay. So this right here is going to be our arctangent. So to summarize then, when y is equal to tangent x, the domain is going to be, well, it was all real numbers except in pi, or no, I don't like that. Let's delete that. It was pi over 2 plus in pi, where n was a integer. We talked about this before. What this is saying is the range is all real numbers except where we had any multiple of pi over 2 and negative pi over 2. That's where the vertical asymptotes are. The reason why we had those was because we would have been dividing by 0 because the cosine's 0 at all those values. The range is just all real numbers. And this gets translated, right, into, oops, I'd start right now, arctangent. But I don't want to write the A, so arctangent. So we're going to get a domain of all real numbers. And our range is going to be restricted to only between negative pi over 2 and pi over 2. And now, if you've been watching the previous two videos, you're going to ask the question, well, here I use parentheses, but if we recall for arcsine, we had a range of negative pi over 2 to pi over 2. So there is a conceptual difference here in notation. The parentheses signify a open interval. The square brackets here signify a closed interval. So here the range, it has to be strictly less than pi over 2. Oops. So all our angles that arctangent gives out are between negative pi over 2 and pi over 2. In fact, I'm going to delete that theta and put in a x. Whereas for arcsine, it actually includes pi over 2 and negative pi over 2. So those square brackets means we are including the endpoints, pi over 2 and negative pi over 2, but when you have parentheses, you do not include the endpoints. That's the difference between open and closed intervals. So be careful about that. The other thing we want to note now is for arctangent is that it will give out angles. That's a terrible line. It's going to give out angles. And that's a terrible circle, unit circle, but we'll run with it. Arctangent gives us angles on the right side of the graph. In fact, it will give you all the angles on the right side of the unit circle except negative pi over 2 and pi over 2. All other angles it will give out though. So that is just something to keep in mind, just visually speaking. That's very useful. Alright, so we got domain and range of arctangent now. So arctangent, in fact, it gives you almost all the angles like arcsine. It's just one includes two more values than the other. Alright, so with that we can conclude our initial discussion on arctangent. If you've been enjoying our videos, please subscribe, consider supporting us on Patreon. Thank you for joining the math party, and I will see you next time.